Okay, so in the last video, we talked about solving problems with constant velocity using the equation for constant velocity. And just to remind you, that equation looks something like this. Okay, so we have, let me smaller. Okay, delta x equals v times t, where delta x is the displacement, v is the velocity, and t is time. Okay, now what we're going to do now is we're going to switch over from using the equation for constant velocity and look at solving problems with the same type of motion using what's called motion graphs. Okay, and just to remind you, constant velocity is a motion where something is not moving any faster or slower, but they're just going forwards or backwards at a steady pace. Okay, so the first thing I want to show you is called position time graph. Okay, so as you're looking at this slide and adding things to your notes, the things that you should pay the most attention to is right here. Okay, so a position time graph is a graph that shows how the position of an object changes over time. Okay, so typically on a position time graph, it looks something like this. On the x-axis, you have time, usually measured in seconds. And on the y-axis, you have x, which is position. And then you get some type of graph that shows you how the position of an object changes with time. Now remember, position is like a single point on a number line. Okay, so if you imagine an object moving backwards and forwards, their position can go up and down depending on where they are along that number line. Okay, now on a position time graph, there's two key elements that you need to know. Okay, number one, the y-intercept of a position time graph tells you where the person or object begins their journey. Okay, so for example, if I had a position time graph that looked like this, okay, I would look right here at the y-intercept, and that would tell me where the object starts. Okay, that's what's called initial position, their starting point. Okay, so that's fact number one. Fact number two, which is more important, is that on a position time graph, if you want to use a position time graph to find the velocity of the object, then what you need to look at is the slope. And slope is something that you should be familiar with from your math classes. Remember that slope of a graph represents the rate of change of the graph, and rate of change of position is velocity. Okay, so that tells you how fast the object is moving and in what direction. Okay, so when I give you a position time graph and I ask you to calculate the velocity, what you're looking for is you're looking at the slope. Okay, remember slope is rise over run. We're going to use these the point slope equation, or not the point slope, the just a regular slope equation to calculate slope here in a minute. Before we do that, I want to show you some simulations of position time graphs. Okay, and we're going to look at these two questions. How can you tell if the object is moving backwards based on the position time graph? And how can you tell if the object is at rest based on the position time graph? Okay, so let's take a look at a simulation. Okay, so this is our moving man simulation, and we've seen this before actually. Okay, so I have the moving man here, and I can make him move backwards and forwards. And what I'm going to show you now is what happens if he moves, let's say, backwards. What does his position time graph look like? Okay, now to give him, or to make him move backwards, that is to the left, I'm going to give him a negative velocity, negative 2 meters per second. Okay, notice where he starts. He's starting at the origin, 0 meters. And so when I hit play, I would expect the y-intercept is going to be right here at 0. And watch what happens. Okay, so notice he's moving to the left. And looking at his position time graph, notice two things. Number one, his position is decreasing. That's because he's moving to the left. Okay, that means this graph has a negative slope because it's going down, right? And also notice that the shape is a line. This is a linear graph right here. Okay. Now when he hits the wall, he's going to stop, and watch what happens after he stops. Okay, so notice his position time graph is still going, right? But now it has gone horizontal because his position is no longer changing. Time is still going on, but he's not moving anymore. Okay, so you should have also learned in math that if you have a flat line, a horizontal line like this, the slope of a horizontal line is 0, right? Because slope is rise over run, and if you don't have any rise because you have a flat line, then you don't have any slope. Okay, so this first segment you would have a negative slope because you have a negative velocity. Over here, this object is not moving because the position is not changing. Okay, now if I reset, okay, let's see what happens if I give him a positive velocity. Now I'm going to make it positive 2 meters per second. And let's see what the position time graph looks like. Now, actually, I'm going to start him off at, let's say, negative 2 meters. Okay, so now he's actually going to start back here. So when I hit play, I would expect his y-intercept to be at negative 2. And because it has a positive velocity, I would expect a straight line graph that has a positive slope. Okay, and that's what you see. And you see his position time graph is going to keep going up until he hits the brick wall over here, and then it's going to level off again. Okay, and now he's at rest, he's stopped, his velocity is 0, and you can see his position is no longer changing. Okay, now just to show you what happens if you change the velocity, here I want you to see how I can adjust the velocity on the velocity time graph and how that changes the position time graph over here. Okay, so notice if I increase the velocity, the position time graph gets steeper, right? Which makes sense because on a position time graph, the slope represents the velocity. If I make the velocity go down to 0, let's say right here, I can't get, there we go. 0, like that, we can see the velocity is 0, and so the position time graph is almost completely flat. And now if I give it a negative velocity, notice the shape is not changing. It's still linear, right? This is still a linear graph, but negative velocity means negative slope. Okay, so this would be going very fast in the negative direction. This would be at rest right here, and then going very fast in the positive direction. Okay, so keep in mind, if velocity is positive, that means you're going in the positive direction, and if velocity is negative, that means you're going in the negative direction. Okay, so again, on a position time graph, make sure you have these two key elements down, draw a box around them, highlight them or something. Okay, position time graph, the y-intercept represents your starting position, the slope represents the velocity of the object. Okay, now the way you calculate slope, you can use rise over run, but what I find is best is to use the slope equation. Okay, the equation for slope looks like this: y2 minus y1 divided by x2 minus x1. Okay, so what you do is you pick 2 points on your graph. It doesn't really matter what 2 points. I usually prefer to do the endpoints, but it doesn't really make a difference. Okay, just like it also doesn't really make a difference which one is point number 1 and which one is point number 2. But if this is point number 1, okay, remember that in math you write using an ordered pair, or you put the x value first and then you put the y value. Okay, so if this point was, let's say, 2, 4, then x1 would be 2 and y1 would be 4. Okay, just to give you an example, it's not actually that point is wrong looking at the graph, but that's just an example. Okay, so you pick your 2 points and then you plug into the slope equation to find the slope. Okay, so now we'll do some examples with that. Okay, so example 1, we have a position time graph. We know it's a position time graph because it says position on the y-axis. Now sometimes it'll say x instead of position, but that's the same thing. That's just a position time graph. And the question says, look at the position time graph shown for a car to the right. What is the starting position of the car based on this graph? Okay, starting position, if we have a position time graph, we are looking at the y-intercept. So I look at my y-intercept, I see it's 0. Okay, and so I would write down x equals 0 is my starting position. X equals 0 meters. Okay, now I would not write down 0, 0 because I really only care about my position, which is on the y-axis, so just one number 0. The second question says, what is the velocity of the car between 0 seconds and 5 seconds? Now remember, on a position time graph, the velocity is represented by the slope. Okay, so what I want to do is I want to look at the graph between 0 seconds, which is right here, and 5 seconds. Okay, so I go along my graph to 5 seconds, that's right here. And if I want the velocity in between those two times, then I need to find the slope. Okay, now because I've already drawn a dot there, I already have my 2 points. I can choose any 2 points I want as long as they lie on the line, but I'm going to use the endpoints in my slope equation. So this is the origin, this is 0, 0. This is 5, 5. And I use my equation for slope. Slope equals y2 minus y1 over x2 minus x1. Okay, I'm going to say this is my point number 1. So this is my x1, this is my y1, this is my x2, this is my y2. It really makes no difference which point is number 1 and which point is number 2 as long as you're consistent. Okay, but the 2's have to go together and the 1's have to go together. Okay, so y2 is 5. So I'm going to do 5 minus y1, which is over here. So 5 minus 0, divided by x2, which is 5, minus x1, which is 0. I get 5 minus 0 is 5, 5 minus 0 is 5, and then 5 divided by 5 is 1. And so the velocity, I would write v equals 1 meter per second. Okay, so this object is traveling forwards. They have a positive velocity, and they're traveling forwards at 1 meter per second, and they keep going like that for 5 seconds. Okay, now the next question says, what is the velocity of the car between 5 and 10 seconds? Okay, so between 5 seconds, that's right here, and 10 seconds, it's right here, what is the car doing? Now we saw this before, but if the position is horizontal, if the position is not changing, that means the object is not moving. And if the object is not moving, then the velocity is 0. Now, if you didn't know that, what you would do is you would still pick 2 points. Let's say this is 5, 5, and let's say this is 10, 5. And you can go to plug into the equation for slope, and you're still going to get 0. Because when you do y2 minus y1, you get 5 minus 5, divided by x2 minus x1, 10 minus 5, and on top 5 minus 5 is 0. And 0 divided by anything is 0, and so either way you would get 0 meters per second. Okay, so in other words, for the first 5 seconds, the car is moving forward, then it stops for 5 seconds, and then the last question says, what is the velocity of the car between 10 and 11 seconds? Okay, so here is 11 seconds right here. Okay, so let's see. I want to choose my 2 points because it's asking me for velocity, and I know on a position time graph the velocity is found by finding the slope. Okay, so I want to find the slope. Right in here, I already have my 2 points picked. I've got 10, 5, and then this is going to be 11, 3. And so again, I go to my slope equation. I identify my points. This is going to be x2, y2, and this is going to be x1, y1. Again, if I had this flipped, it would not make any difference. Okay. The only reason I made this one x2 and this one x1 was because this point comes after this point, but it doesn't really matter. Okay, so I plug into the equation for slope. Y2 minus y1 is 3 minus 5, divided by x2 minus x1. That's 11 minus 10, and that's going to be negative 2, divided by 1, and that's negative 2. Okay, so the velocity of the car between 10 and 11 seconds, I would write v equals negative 2 meters per second. Okay, notice that this is a negative velocity. That means the object is going backwards. And notice that by the time the question is over, they're back to 0 meters. That's where they started from. So in other words, they've gone forward, they stopped for 5 seconds, and now they've gone backwards back to where they started from. Okay, so that's how you would interpret this graph. Okay, so pause it there if you need to write that down. Okay, so I'm going to erase this. Okay, so take a look at example 2. It says, use the position time graph shown to the right to completely describe the motion of this object between 0 and 10 seconds. Okay, so looking at this graph, here's 0 seconds, and here's 10 seconds. Okay, now this is a position time graph because it says so in the question. And just looking at this graph, I know that right here, what is the object doing right here if its position is not changing? Okay, the object is not moving right here. So I at least know that for the last 5 seconds, the object is not moving. It is at rest. What about during the first 5 seconds? Well, I know it's moving at a constant velocity. I know it's constant velocity because the shape of this graph is a line, and that's all we're talking about right now anyway. Okay, so if I want to find what that velocity is, then I need to find the slope. Okay, because on a position time graph, the slope represents the velocity. So I pick 2 points, 0, 0. This is going to be 5, 25. I use my equation for slope. Slope equals y2 minus y1 divided by x2 minus x1. And I go to plug in. It's going to be 25 minus 0 divided by 5 minus 0. And if you calculate that out, you should get 25 over 5, which is 5 meters per second. Okay, and so what I would say in response to this question is I would say for the first 5 seconds, this object is moving forward with a constant velocity of 5 meters per second. Now, how do I know it's moving forwards? Well, because it has a positive velocity. Okay, it has a positive slope. After that, the object remains at rest for another 5 seconds. Okay, so that's how you would completely describe the motion of this object between 0 seconds and 10 seconds. Okay, so pause it there if you need to look at that some more. Okay, so the last thing we're going to look at in this video is velocity time graphs. Okay, so a velocity time graph is exactly what it sounds like. A velocity time graph tells you how the velocity of an object changes over time. Now, if you're talking about an object that is moving at a constant velocity, then what should that graph look like? Well, okay, so velocity time graph would have velocity on the y-axis, time on the x-axis, and if it's constant, that means not changing. Think about what a constant graph looks like. If it's not changing, it would be horizontal, like this. Okay, so that's what a velocity time graph would look like for an object moving at a constant velocity. Okay, so notice that you can have a velocity time graph and a position time graph for the same situation, and they're going to look completely different. Okay, so if I have an object moving with a constant velocity like this, the position time graph might look like that. Okay, so notice the way you interpret these two graphs is completely different. Okay, so pause it there if you need to look at that some more. We'll do some more examples. Okay, and just to go back and show you on the simulation, okay, that's what we saw before. Okay, so notice as I change the velocity time graph, okay, this is still constant velocity because there's no acceleration yet, but as I change the velocity time graph, the shape stays horizontal and the shape of the position time graph stays linear. Okay, so example 10. It says, explain in a complete sentence how the car is moving based on its velocity time graph shown to the right. Well, I would simply say that this object is moving at a constant velocity of 10 meters per second. Now, how do I know it's constant velocity? Well, because I look at the graph and I see the velocity is not changing. How do I know it's 10 meters per second? Because it's constant, and it says 10 right there. Okay, so there you go. That is example 10. And I'm actually going to skip example 11 for right now. And then I think I think that's all the examples that I want to do. Okay, so in this video, after watching this video, you should be able to interpret a position time graph, use a position time graph to find the starting position and the velocity of the object, and you should also be able to draw and interpret a velocity time graph. And again, all of these graphs that we saw today are only for constant velocity. We have not touched acceleration yet. Okay, we will talk about acceleration in the next unit, but for now we're keeping the graphs as simple as possible. Okay, so please let me know if you have any questions, and as always, I will see you guys in the next video.